Still able to listen? Yes. So thank you very much for inviting me, Ricardo and Alessandro, to this workshop. I'm still wondering what you mean by unfitted. So if it's non-fitting, so I feel well here. Yeah, but anyway, you will see that my presentation is in some sense fitting and not fitting to the subjects of this workshop. The isogeometric B-wrap modeling I will focus first of all, and we will see many of these issues that have been mentioned already before, but also I will say something about shape optimization, about topology optimization, which is in some sense not yet, let's say, fitting to what we're doing there, but that's the subject of future work. We'll just try to merge these issues. First of all, IGA, I think I don't have to repeat what that is, introduced by TUM in 2005, and evolving in all fields and directions. And Alessandro is one of the core groups, the European TUM. No, are you? I don't know. Anyway, something like this. With our group, we have been focusing from the very beginning to application issues and technical issues, applying those features, these ideas in large scale, true engineering issues. And there are three things which I mentioned. The shell, which we have been focusing on, the work by Joseph Kindle, also later on a member of Alessandro's group and now professor in Norway, have developed this Kirchhoff-Laff shell. And the work by Michael Breitenberger, which has developed from that the isogeometric B-wrap analysis, which I will just show you in a second. But I also mentioned these two guys, Andreas Apostolatos and Robert Schmidt. Robert Schmidt, who started with this trimming issues, working on the chair. And Andreas is still working on that, still member of the group, he's a mathematician. And he published some years ago already some work about the treatment of these continuity conditions in the weak sense and all these different possibilities which have been mentioned also already today, penalty method, Nietzsche method, Manila Gaussian, all this stuff. So that's the basis where we are there now. Some applications, so that was one of the first applications of the shell of Joseph, which he did together with Uwe Bletzinger in those weeks or months when he had been over there in San Diego. The analysis of these large-scale blade models. Other applications which we just have been working actively at the chair, and I just mentioned Kiwi 3D, a plugin for Rhino 3D, which will just be launched in the next weeks, intended for the use in the vicinity of architecture, with large scale and in particular large deformation analysis of any kind of pieces like this, of wood or textiles, for the intuitive and interactive generation of crazy shapes and crazy structures, not only shapes, crazy structures used in architecture. Perhaps you have heard about active bending. It's one of these hype themes in architecture, where those guys want to do large bending analysis just like clicking keys, and likely in these cut environments which are just given by Rhino. That is the outcome of a DFG, a German research foundation founded piece of work done by Michael Breitenberger. That's basically a 3D puzzle, of shells. So the idea, how can we bring into the actual situation of civil engineering back concrete shells? It's a problem building concrete shells because the formwork is much too expensive, so it makes sense to prefabricate that into smaller pieces, make 3D pieces out of them. There we are. So there we have these trimming operations, these embedded problems, finding also the proper shape of this interaction between this and this member, and then we are already also with questions of optimization, finding the position, finding the shape of these intersection lines to create something which is producible and perhaps also locating this intersection at spaces or locations in that shell where it makes sense to put them. You should not put them everywhere. Or the outcome of a little cooperation with Mercedes-Benz in Sindelfingen, where we just applied this approach to real size engineering pieces, and that's this hood of this Mercedes car. And if you look closely, it's just made of this infinite, almost infinite number of little pieces, trimmed NURBS, surface patches. I personally didn't know that they do these crazy things. I mean, they just do construction of that, and the challenge is obviously clear. How to do analysis with something which looks like that, if you look closely. And you have to formulate or to consider these interactions of these individual pieces, formulate the continuity conditions, deal with non-watertight surfaces or geometries, and so on and so forth. As a matter of fact, we are able to do it. And that, I think, looks a little bit more simpler, but it is not. And it's more or less at the top of everything what we could think in this context. We're dealing here with textile structures, these textile roofs, and as they are made of textile, they're able to transmit compressive stresses and forces, and they are not able to transmit bending. So the shape, to find the shape is the first issue. So we must find the shape acting in tension, and that's what we call form finding. It's a kind of optimization question, finding the optimal shape which suits to a certain stress field in tension. It might be homogeneous, and you end up with a minimal surface, and it might be anisotropic, then you find something else, but it's clearly the outcome of this optimization procedure, finding the shape of equilibrium for a given surface stress. So, and what we're doing here is that we formulate everything in a cut environment, and include the cutting pattern simulation to that. So if you like to build that, you build it typically of pieces of textiles, and they have to be cut in the undeformed reference configuration, you would say, as a mathematician. Then you saw them together, or glue them together nowadays, and you put it in space, and by this deformation procedure, putting it from the undeformed into the deformed situation, then it will unfold to that surface, which will be in that proper shape with the intended field of deformation. So what you see here are the control points in a cut environment. Here are these control points, and you see we just have trimmed those patches, which you don't see, to the remaining cutting pattern. And that's again this optimization problem, another optimization problem, where to put these cutting lines such that after putting them together and putting them into space, the intended shape and stresses just appear. So in that sense, we have two types of trimming problems. This, I would say, is the mechanical trimming option, operation, where we just really have to look for the cutting pattern. That's what you see here. And if you look closely, you see here that we have different parameterizations which don't fit. That's more or less the numerical or the mathematical whatsoever, part of the trimming exercise, where obviously the surface was just composed of not adjacent surface patches, which is the reality. People just put things together, don't care about it all, how they're parameterized. So, and though we have to deal with both of these kind of trimming problems, which basically, of course, are the same. Now, from the mechanical point of view, it's quite interesting, and you see immediately how you may treat non-watertight surfaces. These two edges, they're just apart in the cutting pattern geometry, but they're intended to be together after gluing. So points on either side of these edges are intended to be together, and as that is not possible, and it doesn't make sense on the other side to do this really point-wise, we have to formulate this continuity condition across this open space, and that means, in other sense, having watertight geometries is not necessary. You only have to know which side of the two pieces have to be together after installation. So, and there we are. I don't have to go into much details with that. We have these different kind of spaces, the physical space, the parameter space, and we call it the Gaussian space, which just filled by Ernst. Everything boils down, last not least, into integration of these surfaces, and it's quite important to know how you do this, and typically do this with Gaussian points, and basically it boils down to know about where are the Gaussian points to describe the surface, and which of those we don't need really. So instead of having a body-fitted boundary description, we deal with that one here, where we just have one yard patch, we just have these Boolean operations, just having holes or whatsoever. Just think of this textile problem. You just have this cutting pattern problem. Basically, it boils down into the trimming of the basis functions, the ansatz functions, where we just decide between those points in the structure and not inside the structure, perhaps. You may treat them with this fictitious domain or not, but anyway, we have to come up with that. On top of that, we deal with BREP models typically, and that is quite interesting that we can make use of this information which just drops out of everyday's available cut environments, that the overall body is typically composed in this hierarchical manner from nodes to edges, surfaces, and bodies, and you get everything of that from your cut environment. And you have information about the surfaces, you have information about the trimming line, and that in some sense in three terms. You have the cutting line, or this common line, as a line in one patch, in the parametric space of the one patch, in the parametric space of the other patch available, and you have an extra available in a parametric space of the edge itself. All of these things are available, and it makes sense to use them. So, and what we introduced, or what Uwe Bletzinger did, was he made use of this additional information about this cutting line as a curve parameterization, and that's exactly what he calls the BREP edge elements. On this edge element there, typically, of course, you're just formulating these boundary conditions, perhaps here in terms of this penalty approach, which just appears to be quite nice for all kinds of applications, including, of course, implicit dynamics. From our experiences, I just agree to you, we don't need more than penalty formulations, or other way around. They just can be used for many kind of applications. So that more or less, just summarize that. I don't have to go through this, it's clear to everybody, to you. So, making that operational, that's something what we propose, and we'll just publish a paper pretty soon about that, is the format, the format about how you can just model or just bring this trimmed BREP model into operation. And last but not least, it appears that it is at the very end not more necessary than having a list of these Gaussian points for the integration, and relate to the Gaussian point the information about the surface in terms of the trial function, whatever you need. And by that you just turn the typical finite element program to upside down. Instead of formulating all the elements and going down into the Gaussian points, you just go through the loop. You just have a list of the Gaussian points which you just operate and get from each Gaussian point all the necessary information regarding geometry and the ansatz functions and whatsoever like that. So that is formulated, nicely arranged in a data format which is available, and also already implemented in GID, at least in a trial situation, and you can just try to do it. Here you see these implementations from cut to cut. The geometric design to the simulation. Inside there, of course, we have some solvers. We have our own software, Karat++, and we intensively cooperate with the guys here from Sydney, Ricardo and Pujan, and we're also part of this Kratos group in the meantime, or we just implement or just have made that thing running in the large space. You see more or less in gray, yeah? We will pretty soon have a cooperation with LSTC and Dyna, where we just try to bring this data format into operation in the larger sense. Yeah, that more or less summarizes the procedure. We have the initial cut geometry, where we just add some additional information about the loading, and the boundary conditions, and the continuity conditions. Yeah. Then we have this individual parameterizations of the packs, as you see. Yeah, here we have the trimming edge with the individual surface parameterizations. On that top we can also do refinement, and everything is driven by the information of the integration point, the Gaussian point, which, as I said, are just the basis of everything what is done. And last but not least, that's how we see it. Yeah? That's how we see the problem. In that sense, it's brought down into some logical operations, inside, outside, or on the surface, not on the surface, and we are able to do the simulation. We came from a totally different direction, I would say, but we arrived at the same end, and it's not surprising, obviously, of course. Yeah, and so far we share insights and knowledge, also coming from different positions. Here you see comparisons with standard final element approaches. Not surprisingly, they meet, of course, the results. And here you see the full engine hood here from this Mercedes-Benz car. And here, typical application, which we did also for Mercedes-Benz. They are interested in a very early stage of engineering of this car about information, if these geometries might be able to be deep drawn or not. Yeah? It's of course a plastic problem, deep drawing, but it was surprising for me. They have so much knowledge and databases available that they're able to do linear elastic simulations with typical efficient, effective load cases to get this information. If that might be deep drawn or not from a linear elastic simulation. So, and the idea is just having available the CAD model, do this test on the CAD model, we get the result from that, and go on with the generation of your model. So, another topic which we treat together with BMW is the CAD reconstruction after shape optimization. So that's what I mean, that's the unfitted part of the lecture, something about shape optimization. And what we're doing is that we just implicitly formulate the shape velocity fields through a design control field, which we just filter by some filter, and from what we just generate in the second step the geometry, and taking derivatives of that, we have an implicit definition of shape velocity fields, allowing us to deal with almost infinite number of design degrees of freedom optimization. And we call it vertex morphing because in the discrete manner we deal with more or less discontinuous C0 shape function, and we have vertices. A little application for BMW, the shape optimization of these air ducts for the defrosting of the windshield, to optimize that. And here you see the workflow, starting with the initial cut. Then we have still the typical standard element model from which we do the shape optimization, where each of these nodes are able to allow to move in space. And there you see we have an infinite, very large number of design spaces. The largest we ever did had more than 3 million, 3.5 million degrees of shape, a number of shape variables. And from that, we just retrieve the cut model. And there again, we make use of trimmed surfaces, just to treat that, to bring that back into something which is suitable for the designer. So typical trimmed surfaces, and the good information that the surface quality is really most impressive if we do that. That also works for solid models, not only for surfaces, which also says that we have nothing to also regarding this eyebrush stuff, at least for the surfaces of 3D. That's collaboration with Siemens. Siemens, we use Siemens NX, of course, as CAD environment, and Kratos at the solver for the industrial approach to shape optimization. And that's demonstrated for Siemens, although that's the back door of the BMW Cartman Mini, and you see we can just by one click activate those regions which should be optimized. Of course, again you see trimmed patches of this cut model, and then we have by our vertex morphing method just only one typical parameter to be set to come up with the optimization. In blue you see the optimized shape, and in gray the initial one, and you see there's no limitation for the size and the shape of the structure to do optimization. I would like to end with this figure showing you what we're doing together with Honora for the shape optimization of entire airplanes. Just now in the trial state we have 80,000 shape variables. The optimization is done in the standard finite volume mesh, but with respect to the design, the intersection of the wing with the fuselage, that's the problem. And that's typically not possible to come up with standard parameterization of the surface with NURBS patches. And there you see all these issues just come together, dealing with these trimmed intersections of the cut model, which should be finally the outcome of this procedure as the basis for further engineering. And we just use this vertex morphing method to come up with information about the shape, coming up with the IBRA for the identification of the cut model, taking consideration these intersections and these trimming operations, and so non-fitting things may fit into the subject of this workshop. Okay, that's more or less what I wanted to say, giving some motivation and inspiration for further things, and that's what you're working on. Ready?